Hello, I'm Minyoung Park, a master's student in the TM Lab from Dongguk University. In the seminar, I'll be reviewing a paper that names of a novel integrate approach for road mapping disruptive technologies from a technology convergence perspective. The presentation outline follows the structure of the paper. This paper, published in IEEE Transactions Q1 Journal, tracks the evolutionary paths of disruptive technology convergence in smartphones and presents a roadmap to guide future technology development and R&D decisions. Unlike traditional technology road mapping, which broadly categorizes trends, this approach provides a detailed analysis at the material level, offering a clear view of the evolution of each component. The first section is the introduction. A technology roadmap is crucial for analyzing the relationships between technology, goals, and environmental changes, visually mapping technology evolution. Originally for tech product market analysis, it now includes data-driven methods like patent analysis and text mining. Traditional SIU-based text mining captures functional relationships but misses structure ones. The TRT structure addresses this, but combining SIO and TRT is still limited. The SIOPP structure overcomes this by integrating prepositional phrases with SIO elements for a more detailed analysis of technological relationships. This study combines SIOPP-based analysis with TRM to monitor disruptive technology evolution. Unlike traditional methods, it analyzes both functional and structural relationships, offering a clear understanding of technological trends and future developments. Moving on to the related work section, for technology convergence measurement, this study proposes an SIOPP-based method to measure technology convergence in disruptive technologies. While traditional methods rely on expert opinions or patent analysis, this approach combines the functional relationships of SIO with the structure insights of propositional phrases. This enables a more precise evaluation of DT evolution, forecasting innovation, and guiding future technology development. And for DT road mapping, to understand the evolution of disruptive technologies, technology road mapping is used to track advancements by mapping relationships between technology, goals, and environments. Traditional TRM relies on expert judgment, but objective methods like patent analysis and SIO-based text mining complement it. The TRT structure captures structure relationships, while SIO focuses on functional ones. This study introduces the SIO-PP method, combining both to analyzing functional and structural relationships, offering a more accurate understanding of technology convergence and future trends. Next is methodology. This research framework includes four stages. First, patent data collection and pre-processing. Second, classification of DT lifecycle stages. Third, identification of key convergent technologies. And fourth, Construction of a DT technology convergence roadmap. The research questions are classify DT patent life cycles and identify emerging convergent technologies, analyzing evolutionary patterns of new convergent technologies, extract key convergence relationships using patent networks, develop an SIOPP-based roadmap, and analyze functional and performance evolutions of DTs. The last one is apply three principles to identify trends in DT technology evolution. The first step is patent data collection and pre-processing. Relevant patent data was gathered and text mining was applied to extract key functional and performance characteristics of DTs. The dataset includes IPC codes and priority years for analyzing DT technology, domains, and convergence trends. The next step is division of DT life cycles. To improve classification accuracy, S-curve modeling was used with patent and market data to estimate DT development speed. Growth rates changes in cumulative patent numbers helped infer the life cycle. The market data was combined to enhance classification accuracy. Step 3 is identification of key convergence technology in DTs. IPC codes from the first year are considered existing technologies, while those emerging in subsequent years are defined as new convergence technologies. For growth and impact analysis, we monitor the evolution of new technology by analyzing growth in authenticity and impact. Growth is classified into five categories: emerging, sustainable and increase, sustainable and stable, sustainable and decrease, and decline. Impact is measured through IPC co-occurrence networks using metrics like closeness, centrality, betweenness, centrality, eigenvector centrality, and structural holes. The top-6 method is used to objectively evaluate and identify high-impact emerging convergent technologies. Key convergent technologies were identified through growth and impact analysis. The top 10 technologies with the highest impact at each DT lifecycle stage were selected and classified as either sustainable and increase or sustainable and stable. In step 3.4, the roadmap for key technology convergence evolutionary pathways was developed. Key technology relationships were extracted using IPC code pairs and Python, then visualized with GetPy and clustered with the Luvian algorithm. SAUPP analysis classified technology topics and identified convergence drivers. The TRM framework analyzed technology topics with the evolution of DT functions and performance maps along the horizontal axis. The roadmap was developed by aggregating major technology topics to show convergence evolution across the DT lifecycle stages. Using trees theory, they analyzed the laws of technological system evolution to identify regular patterns and future trends in DTs. By applying trees' 8 laws, they quantitatively assessed DT's evolutionary characteristics, predicting future evolution paths. This provides valuable insights for R&D decision makers and policymakers supporting practical application. For case study, patent data from the DII database, 265.32 patents from 1994 2021 were analyzed. Patents with multiple IPC codes were considered convergent. S-curve modeling and derivative analysis were used to identify technology evolution patterns, and predict future trends in smartphone development. The analysis of smartphone technology lifecycle stages identified key convergent technology as shown as key technologies like touch panels and information processing emerged early, with medical technologies gaining importance later. Touch panels and MEMS were the most influential technologies driving smartphone innovation. Smartphone technology evolved through convergences in touch panels, batteries, communication, cameras, and software. Touch panel tech progressed from resistive to capacitive, acoustic wave, and flexible systems. Convergence occurred in screen manufacturing, photosensitive materials, and silicon treatments, transitioning from light-emitting materials to conductive fibers, shock-absorbing materials, and optical adhesive. For the discussion and conclusion, the study proposed a framework for analyzing technology convergence using smartphones as a case study. It integrates patent code classification, SAOPP analysis, and TRM to track convergence and DT development. Identifying eight evolution paths, trees theory was used to predict future trends. For the limitation, the framework was validated for smartphones, but its applicability to other sectors is unverified. So future research should test it across industries to enhance its generalizations for DT studies. Thank you for listening to my presentation.